My name is Jim Turek. I'm the session chair of Session 4, Track 4, entitled Migratory Fish Benefits Derived from Fish Passage Restoration. What are we learning? Where are we headed? My co-presenters and I very much appreciate you joining us today with your busy schedules and the great challenges we face with the pandemic. Please now allow me to provide you with a brief summary of information for this session. For those of you who are engaged in fish passage restoration, you know the significant challenges that we face to restore rivers and migratory runs, often to even a small fraction of once magnificent runs. And although there are tens of thousands of dams throughout the U.S., we are making progress to remove these impediments and implement other restoration passage types to restore healthy, self-sustaining fish runs. My co-presenters and I would like to briefly familiarize you with the migratory fishes that we will be highlighting this afternoon. We'll be focusing on 3 anadromous fish species, including alewife, blueback herring, and American shad. These fishes spend much of their lives in coastal and marine waters, with adults returning to their natal rivers and streams to spawn, and sometimes returning multiple years. Juveniles remaining in rivers, streams, and quiet waters, typically for 6 months or less, before leaving for their multi-year oceanic journeys. Our session focuses on 4 questions to be addressed by our collective presentations, with a theme centered on restoring robust populations of migratory fishes serving as keystone species and supporting healthy marine and freshwater ecosystems. We believe these questions highlight topics which many fish passage restoration practitioners seek to answer or secure information invaluable to watershed management, program and project funding, and natural resource and land use policy decisions. Our highly talented and experienced team of 4 is looking forward to presenting to you all this afternoon. We hope you'll learn from our knowledge, experiences, and presentations, and the information is valuable to your restoration projects or other career or academic interests. And now our first presenter, Ms. Abigail Archer. Thanks all.
Good afternoon. My name is Abigail Franklin Archer, and I'm an extension agent with Woodsole Sea Grant and Barnstable County Cape Cod Cooperative Extension. And I'm going to tell you about a before and after dam removal fish passage study. The study species is river herring, and the telemetry study was done at Town Brook, which is a small river which is part of a small coastal watershed in Massachusetts. Our study area is part of the Gulf of Maine, and where the star is, that's Plymouth, Massachusetts, and that's partway between Massachusetts Bay and Cape Cod Bay systems. So we'll zoom in a little bit, and you can see that it's a pretty short river. It's a first order stream with a watershed of 10 kilometers squared. It's only 2.6 kilometers long, and its headwaters are at a 109 hectare freshwater lake. And it's called Billington Sea, but it is actually freshwater. And you can see that it's an urban watershed. And this river has a river herring run. So thanks to the dedication of volunteers at the town of Plymouth, we know from a volunteer visual count that's done using a Division of Marine Fisheries protocol that, so in counting upstream migration of adults, we know that the population estimate has ranged from 107,000 to 230,000 river herring from 2008 up to 2020. So there's been quite a bit of restoration taking place on this river over the years. For a short river, it's had a lot of dams. There were 6 dams along this river. 5 of them have been removed. There's just 1 remaining at Jenny Grist Mill. If you'd like to learn more about the restoration work that has taken place on this river, I encourage you to check out the NOAA story map, which is called Swimming Upstream, journey through 20 years of restoration in Town Brook in historic Plymouth, Massachusetts. And then also Malona McBroom, which is the engineering firm that designed the river restoration projects. They have a flyover video that shows you the different restoration projects over the years. But we're going to focus on the Holmes Dam, which was removed in 2018 and 2019. And then I'll touch just a little bit on the Jenny Gristmill Dam, which is still present. And there's a steep pass fish ladder there. So from a fish's point of view, if you were traveling upstream, if you wanted to get past the Holmes Dam, you would need to move upstream through this steep pass that it's in the bottom left, travel underneath a road, and then ascend through a 202-foot long Daniil fish ladder, and then go through a short section of Pool and Weir fish ladder, and then land in the mill pond. Of course, then you'd still have more river sections to go through to get to the spawning pond. So when the town of Plymouth was able to access funding to remove the dam, they knew that they wanted to know what fish passage was through this section of river, both before the dam removal and after the dam removal. So they contacted me to discuss this many years before construction started. The construction was funded by NOAA, U.S. Fish and Wildlife Service, the Massachusetts Division of Ecological Restoration, and the town of Plymouth. And then the fish passage evaluation was funded by Woods Hole Sea Grant, U.S. Fish and Wildlife Service, Town of Plymouth, and then with a tremendous amount of in-kind support and technical assistance from USGS and Division of Marine Fisheries, and also some in-kind support from NOAA. The dam was 16 feet tall and 175 feet long, and the impoundment was 67 acre-feet. So the study question is, will the removal of Holmes Dam improve passage of river herring? And we wanted to know this, if this is true, through the newly restored section of river, and then also all the way up to the spawning pond at Billington Sea. The tool we chose for this was passive integrated transponder telemetry. And if you have ever had an Easy Pass transponder or sticker on your car and driven through a toll, then you have interacted with this technology. So the idea is that you tag the river herring with a small tag internally, and then you allow them to swim through the section of river of interest. But along that section, you have gates or tolls, or I call them antennas. And so it's loops of wire encased here in PVC, and then it's connected to equipment that allows us to figure out where those tagged fish, what gate they went through at what time. We're able to track the fish's movements. So that's the technical side, but how do you actually quantify improved fish passage? How do you know that it's improved? So there's 3 metrics that I'm going to use to describe it. The first is percent passage. So if you have 10 fish that potentially want to move upstream past a fish ladder, and then only all 10 of them try, but only 4 of them make it past, then that gives you 40% passage. The next is passage attempts. So the question is, did a fish try once and succeed, or did they try multiple times? So this fish was successful, and he or she just made 1 attempt. Now this fish is going to make 1, 2, 3 attempts to get up the fish ladder. So he was successful, but it took him 3 attempts. And then the last metric is transit time. So how much time did it actually take a fish to swim through the entire fish ladder? So because the fish are tagged, we know exactly when they go through a gate or an antenna, and then there's a timestamp. So this fish entered the fish ladder at 8 a.m. It left the fish ladder at 8:05, and then just by the subtraction, we know that it took the fish 5 minutes. So to track the movements of fish through this stretch of river before the dam was removed, we set up a series of 7 antennas. So we released 312 fish down here, and then antenna 1 allowed us to know what fish were available to pass, that they wanted to move upstream. And then these antennas monitor the steep pass, and then antennas monitored the Daniil fish ladder, and then the small Pool and Weir, And then if the fish gets up to this section at antenna 7, then they've entered into the mill pond and we consider them successful. So the results before the dam removal were that we had 269 fish start to move upstream, but only 67 of them made it up to the mill pond. So that's percent passage of only 25%. So then the dam was removed. So you can see what it used to look like in the top left. The yellow stars will orient you, and you can see that now we have a restored river. The dam is just below the star here, so that's the remnants of the dam. So from a fish's point of view, and no longer do they have to travel upstream through a steep pass, it's now a full stream box culvert. And instead of having the antenna on the fish ladder itself, the antenna is stretched across the entire river. So it's a full stream antenna. Instead of a Juvenile fish ladder, the fish now get to move upstream through a fully restored river with some rock weirs to allow them to overcome the elevation. And again, the antenna 3, instead of being on the Juvenile fish ladder, is now stretched across the full river. So now we'll show you the results with the before dam removal and then the after dam removal, so in direct comparison. So before dam removal, we know that the percent passage was 25%. After dam removal, it was 92%. So on the top right corner, you can see that we attempted to we did get the antennas as close to the original locations as possible, even though we were dealing with a fully restored stream rather than a fish ladder. So 386 fish began their journey up this stretch, and 354 fish made it past where the dam used to be. For attempts, we had a range of 1 and 9 attempts made before the fish successfully moved past the dam. After dam removal, the range was shrunk to between 1 and 4 attempts to successfully ascend past the dam. Transit time, there was a range of 30 minutes to 28.8 hours, with a median of 1.8 hours and an average of 4 hours. The after data is quite dramatic. So the range is 18 minutes to 9 hours, but the median is then measured in minutes. So the median is 38 minutes and the average was 53 minutes. So did they get to the spawning pond? That's the central question. We want to know, were they able to get up to the area where they can reproduce? So before was 22.3%, after was 82.6%. Because we, in addition to having antennas monitoring the section that was newly restored, we also put an antenna close up to the spawning pond. And so we were able to determine how many fish got into the spawning pond and then went back out and headed out to the ocean. So before dam removal, 48% of the fish that entered into the pond then left and headed back out to the ocean, or were detected heading out back to the ocean. The range of time they spent in the pond was 4.3 to 22.8 days, with an average and a median of about 12 days. After dam removal, 76% of the fish, after spending time in the spawning pond, moved back out to the ocean, with a range of 5 to 40 days and an average and a median of 21 days. We detected some repeat spawners, and these are fish that were tagged in 2018 and then detected in 2019. There were 74 of them, and that represented about 15% of the fish that were tagged in 2018. We added an antenna at the mouth of the river in 2019, and so there were 17 fish that were detected, so the repeat spawners that were detected at the mouth of the river, then detected going into the spawning pond, detected leaving the pond, and then detected leaving the river. And of those 17 fish, their total freshwater residence time, so both in the pond and in the river, ranged from 20 to 32 days. So the restoration associated with the Holmes Dam removal was successful. However, there is still one more dam left on Town Brook, and we evaluated this as well with pit telemetry. And in 2018, percent passage was about 60%, In 2019, the estimate was 73%. And we were also able to detect the repeat spawners going through this section. And that data is important because they had not been recently tagged. They had just come from the ocean, so they did not have a tagging effect. And their percent passage estimate was 72% as well. So there is a large portion of the fish entering in the river that are not able to get upstream to the spawning pond right now. So because I'm an extension agent with a Sea Grant program, all of this data is also going to be accompanied by some lesson plans for K through 12 students. The middle school lesson plans are the students are going to be given data and then a map so that they can map the tracks of the fish both before and after, develop hypotheses, and then see if the data supports those hypotheses. And then for high school, we've developed a couple of kits with radio frequency identification or PIT telemetry equipment. And this is going to be focused on students who are in technical schools and engineering classes, and allow them to experiment with the equipment as well. And so these lesson plans are being developed, and they'll be made available online probably within the next year. So in conclusion, PIT telemetry is a useful tool for fish passage evaluations. You can get fine scale data through fish ladders, and it's ideal for small streams. The removal of Holmes Dam did improve passage of river herring, both through the restored section of river and all the way up to the spawning pond. But an impediment to passage does still exist, which prevents about a quarter to a third of the adults from moving upstream. System level improvements and detecting it just takes time and continued financial and people effort to do the restoration and the evaluation and the monitoring that allows you to figure out if it's having an effect. So it's been over 20 years for Town Brook. We don't yet know if there are population level effects based on this restoration, but we do have monitoring in place to detect it. If getting more adults into the spawning pond is the major driver of population size, then we'd expect to see an increase in returning adult herring starting in spring of 2021. But there are many other things that could be affecting population size. There could be ocean effects. It could also be spawning pond habitat quality for juveniles. That could also determine the future population size. So it's important to look at the system as a whole, also all of the life stages of river herring, to see if restoration is improving their population size. And my colleague Matt Devine is going to be giving a presentation later in the session talking about just that, how you can measure restoration effects on juvenile river herring. Thank you very much for your time.
Hello, I'm Alex Harrow. I'm a research ecologist with the USGS S.O. Conti Anadromous Fish Lab in Turners Falls, Mass. Today I'm going to be talking to you about a project that we did on the Pawcatuck River to evaluate dam removals and existing fish passage structures on the Pawcatuck River in Rhode Island. I'd first like to thank my project partners for this project, the NOAA National Marine Fisheries Service, University of Rhode Island Department of Environmental Management, and the U.S. Fish and Wildlife Service. So to give you some background, there's been an active dam removal program on the Pawcatuck that was initiated in 2006 to remove several dams on the main stem and to construct or improve technical fishways at the two remaining dams. And on the left, I've just got a graphic of the lower Pawcatuck River here in southern Rhode Island with the removed dams and some of the remaining dams shown, but also the habitats associated with freeing up that section of the river, both in terms of the main stem and some of the tributaries. Now, since the project's been initiated, there hasn't been any quantitative evaluation of the passage performance of the removed or improved structures. So we decided it would be a good idea to try to get some numbers on how well fish are getting past some of these improved or removed dam sites. So our objectives were to evaluate the movement and passage of adult upstream migrating alewife and American shad past these structures, and then also assess the value of the telemetry as a tool for passage evaluation. There's many ways to do passage evaluation. Telemetry is only one of them. And then I'm going to try to speculate a little bit on the prospects for alewife and American shad restoration on the Pawcatuck once we get those numbers together. So the study site itself was the lower Pawcatuck main stem, again between the states of Connecticut and Rhode Island. There are 3 primary alewife spawning ponds that we'd like to try to get fish to. There's Chapman Pond, Watchog Pond, and Warden Pond at the uppermost end of the main stem. But we know alewife can also spawn in slow-moving sections of the main stem as well. The existing barriers, remaining dams that are still there now, are the Potter Hill Dam and Fishway, the Cronin USGS Stream Gauging Weir, and the Horseshoe Falls Dam and Fishway. So these are the existing barriers. The Potter Hill Dam has a 3 or 4 foot wide Daniil fishway on it, installed in 1972. Farther upstream is the Cronin USGS Stream Gauging Weir, which at high flows doesn't present much of a barrier to passing fish, but at lower flows the head drop is much greater and may present somewhat of a hydraulic or depth barrier. The Horseshoe Dam and Fishway was installed in 2012. It's a pretty much modern Daniil type fishway, but it has many switchbacks. It's relatively long. It's about 15 feet of vertical height. There's also an eel pass installed on this fishway as well. So along with the removed barriers, or in addition to the existing barriers in yellow here, the removed barriers are the green White Rock, which was removed in 2015, Bradford removed in 2018, Lower Shannock removed in 2012, and Kenyon Mills removed in 2013. And these are what they look like. White Rock, pretty much full dam removal, very little head drop across the previous dam site. Bradford was constructed with rock weirs that span the entire width of the river, and there is low points within those rock weirs that the fish can pass through. Lower Shannock was again a straight removal, but with some alteration of the stream bed. It has a little bit higher gradient than Bradford does, and a deep pool immediately downstream of the removal. And then Kenyon Mills, again, another rock weir type structure, very much like Bradford. So we set out to get a hold of some fish and start tagging them. First we had to collect them, which we did at Potter Hill. There's a fishway there, of course, with a trap on it. We could collect upstream migrating fish as they came into the river, at the lower end of the river, and tag them either with radio tags or with pit tags. And then we had fixed monitoring stations that were located at each barrier site, usually above or below the site, in both, so that we could detect when fish were arriving at the dam and then when they actually passed the dam. So that consisted of a radio telemetry receiver in an enclosure and an aerial antenna pointed across the stream that would let us know when a fish showed up. So our collection site, again, Potter Hill Dam and Fishway. The release site for alewife was these 3 locations, and we tried to spread alewife out within the watershed, because if we just released them in the lower watershed, we weren't sure how many would actually make it up to the upper sites. So we hedged our bets, distributed them in 3 locations in the fishway, or in the river system. So I think we did a pretty good job of putting our eggs in multiple baskets. The shad were only tagged and released from the Potter Hill site, and I will say that shad were only tagged with radio tags and not with pit tags, simply because there's not many shad returning to the system. We didn't want to load them up with a lot of hardware, so they just got radio tags. And these are some of the numbers that we released. About 100 alewife got radio tags in both 2018 and 2019. 200 or so got pit tags in each year, and then only 40 odd American shad were radio tagged in 2018 and 2019. So these are the results, and we'll get right to them. We certainly had a lot more data to collect than just these percent passage data, but these are the important bits. So White Rock, again in green, That's a removal site. Potter Hill is an existing dam with a fishway. Bradford, removal. Cronin, the gauging weir, etc. So in both 2018 and 2019, White Rock passed 100% of the fish, which is not surprising. It doesn't present much of a barrier if you remember back to that photograph. Potter Hill, though, we had 0% of the radio tag fish pass. However, of the pit tag fish that we released, we had 61 to 41% pass in 2018 and 2019. So there's a difference between the data that you get back from radio tag fish versus pit tag fish. That's due to handling effect. It's due to the size of the tag. So we're pretty cautious about interpreting some of these data here, but on the whole, I think our radio tag data are at least conservative. So the actual percent passages are probably higher than some of these numbers here. So Bradford was pretty good, 66 to 100%. Cronin, 87 to 96%. Lower Shannock, 70 to 72%. Horseshoe Falls had again lower radio tag passage, higher pit tag passage. The American shad, again, we released those from Potter Hill. A few showed up at Bradford in 2018, but only 9%. In 2019, we had about 43% show up. But oddly, not many fish progressed much beyond Bradford. Although we know they could get past it, few went up to Cronin, only one in 2018 and none in 2019. So a little puzzled by that, why they wouldn't keep going upstream, but I think we have a somewhat of an answer to that, which I'll get to in just a bit. The potential cumulative proportion of fish can then be calculated, at least for alewife, throughout the watershed. So if we take the average of the 2018 and 2019, what I call best data, that is for White Rock, the radio tag data, but for the fishway sites like Potter Hill and Horseshoe Falls, we just use the pit tag data. We can calculate out those averages and then derive a cumulative proportion of fish that are moving up to each upstream site. So in the end, we get about 20% of the fish moving up to Kenyon Mills. You have to remember, though, that some fish are peeling off and going into Chapman Pond or Watchog Pond and Warden Pond. So we don't expect all of the fish to go all the way up to Kenyon Mills. They're stopping, they're spawning in these ponds or in the river itself. But 20% up to Warden Pond is not bad. It's not a bad number for fish to make it up to. So then our question was, what happened to the shad? And we basically investigated this by doing some mobile tracking, took some receivers out in canoes and drifted the section between Bradford and Potter Hill. And from that, we basically got these kinds of data where we saw lots of concentrations of fish between below Bradford and about halfway between Bradford and Potter Hill in sort of these deep, slow-moving sections of the river. And that was consistent every time we drifted through this. We found those fish there. They were active fish. They weren't dropped or dead fish. They were always moving around a bit. So we knew they were real fish just hanging out in these lower sections. And in 2019, we kind of got the same results, the same concentrations of fish below Bradford, and then in this sort of oxbow section in here. So it seems to be real, and it seems that the fish at shad basically don't feel much like going above Bradford. They can if they want to, but for some reason they stay within this reach. And it's likely that they may be spawning in this reach, particularly below Bradford, because we would see a lot of these fish moving up at night and hanging out in what we would call pretty good spawning habitat below Bradford, but we'd have to verify that. So in conclusion, passage of at least the alewife at the removed dams was higher than in the existing dam with fishways, and this is pretty much a trend that we're seeing now. Fishways can pass fish, but it's not anywhere near as good as removing a dam if it's done well. At the stream gauging weir, passage was relatively high, but it may be lower at lower flows. Unfortunately, we did not get an opportunity to monitor lower flows because we had pretty high flow years in both 2018 and 19. So that remains a question, whether that becomes a barrier when there's a low flow year. Shadow past Bradford, but don't ascend much higher in this watershed. There are a few shad hangouts below Bradford that seem to be relatively consistent. I didn't talk much about delays, but fish are delayed both at the fishways and at the removed structures. It happens, and the delays can range from hours to a week or more. Is it a problem? Maybe, maybe not, but it's certainly higher at fishways than at the removed structures. So with respect to evaluation and restoration, we know that telemetry is a pretty precise tool for passage monitoring. We can get real numbers with error estimates around them, but we have to make sure we're using the right telemetry. That is pit tag for small-scale structures like fishways, and radio telemetry for monitoring in whole reaches of rivers. We know there's some effects of telemetry on behavior that we have to account for as well. Multi-year studies are always valuable. More data, more consistency lends confidence to our results. And removal of the dams in Pawcatuck should probably increase survival and reproduction of both species. Potter Hill Dam remains the greatest bottleneck. Again, 50% of the fish can't make it past. It's a lowermost dam, so it's a problem. But luckily, this past August, NOAA awarded the town of Westerly with a 3-year grant to address removal of the Potter Hill Dam. So with luck, we may see the Potter Hill Dam removed in the near future. So with that, I'll stop. I'll take any questions if there are any.
Hello and good afternoon, everybody. My name is Matt Devine. I'm a third-year PhD student at the University of Massachusetts Amherst in the Department of Environmental Conservation. And I'm really excited and grateful today to take this opportunity to give you a little flavor into the work I did for my master's and now I'm diving into with my dissertation, looking at the population dynamics and the restoration ecology of anadromous river herring in coastal New England. Specifically, I focus on the early life history stage, so larval and juvenile fish, river herring, in their freshwater environments. And I look to make relationships between adults and juveniles, between environmental conditions, and understand what the juveniles are doing when they're in these freshwater habitats. And ultimately, to be able to use this information and apply it to restoration, to understand and what the expectations might be as we continue to remove dams and provide fish passage for river herring. So before I dive in, I just want to acknowledge our incredible funding sources and collaborators. One thing I have to note is that this is a spectacular project to be a part of because there's so many wonderful women and men across New England that I've gotten to partner with. This includes state agency folks, federal agencies, nonprofits, lake and watershed associations, and just interested citizens wanting to volunteer. So big group of folks all on board to help recover river herring. It's a great, great, great project to be a part of. So let's dive in. Literally, I'd like to take you underwater here. This is the North Shore of Massachusetts in the Parker River. And you see this really benign environment above water. And then as soon as you go under, it's this chaotic and frantic scene of river herring adults trying to push back up to their spawning ground where they were born 3 to 4 years prior. This is a fascinating phenomenon. If you hadn't had a chance to sit along a stream or a river where river herring run and watch this in action, I highly encourage you to do it. It's pretty neat. Not only is it neat, but this is where we generate most of the data used for stock assessments for river herring. We gather that from adult run counts as they migrate up the river. This is done a number of ways, including electronic counting systems, video counting systems, and citizen science. You know, folks sitting on buckets, counting and tallying fish as they pass through the system. Now, this provides really a wealth of data on the number of adults that return, the timing of these returns, and the size and age structure. But there are data gaps and uncertainties, if you will, as fish can be double counted as they pass up and down. Sometimes fish migrate under the cover of darkness, and if there's not a counting system in place at night, then you miss those counts. So my research has really looked at the black box that is what's happening in the freshwater environment. So we know that river herring are born in high densities in freshwater. They emigrate into rivers and estuaries where they grow in size. but also their numbers decline because they become eaten by more and more predators. And then they eventually mingle at sea with other fishes, and they experience mortality at every step of the way. And it's not until here at age 4 when they return where they're counted by means we just discussed in the previous slide. And so what's missing in all this are estimates of recruitment, or how many fish there are initially recruited into these freshwater lakes. And without that, you really can't understand, almost impossible to understand, where the different sources of mortality are coming from. So my research really makes the case that not only should we count adults, but we should couple that with monitoring and surveys in freshwater of juveniles. So some of the research objectives I'm going to touch on today, and we've, as a lab group, explored. Well, first, we wanted to evaluate what sampling methods we might be able to use for estimating juvenile densities in freshwater. First of all, is it even possible? If so, what sampling gear can we use, and how much effort do we need to apply, and then when should we sample? All unknown questions as of our research. We wanted to investigate density, growth, and mortality, some of these really important demographic rates in these systems, and understand and ask questions about how they vary from site to site. We wanted to look at relationships between adults and juveniles, and then ultimately use this information to determine what we can expect in terms of the magnitude and the timing of a river herring recovery in systems that have had recent restorations, particularly dam removals and fish passage installations. So we undertook a large study of lakes spanning a large geographic area. So from 2014 to current, we sampled 32 lakes across coastal New England from Connecticut to Maine. 5 of these lakes we sampled all years, and so I'm going to refer to these lakes as our long-term monitoring sites. All of these sites, all 32, had a way to count adults to provide an estimate. Some are stocked, some have natural runs where fish pass through fishways, and they vary in physical and chemical habitat characteristics. And I'm going to highlight 2 dam removals and then a fish ladder installation as well. So step 1, we developed a survey methodology. We used a pelagic purseine. This is typically an ocean-going gear used at sea for mackerel and tuna and Atlantic herring. We had one custom made for our freshwater purposes, and you can see the gang deploying it here. And we did this 3 to 10 times in each lake at night in June, July, and August in random sampling locations. After each haul, we would count all the herring and then retain a subsample for age and growth information. To give you a little sense of how this gear works, you can see working from top left to bottom right, it's deployed in a circle. It's cinched in from the bottom, and the fish are essentially trapped in the bottom, and there's buoys on top so they can't jump over. It's pulled into a little half circle right alongside the boat, where then we can dip net the fish that we want to retain and work up and process, and then we can release the other fish after being counted right back into the lake. So it's really non-invasive and provides limited mortality and limited stress on these individuals, which is really important when working with these fish. So what we found was one of our most important results was that, yes, the purseine is effective, but specifically doing it at night, deploying it at night, and in June and July, early summer, is when you get the most bang for your buck with this sampling gear. And so we had the highest catch rates, represented by these gray bars here, in June and July, with the greatest precision, also in June and July, represented by this black dotted line. Precision is important because it's an estimate of repeatability, and that's important when we wanted to end up doing our population modeling. So we were able to publish this work in the North American Journal of Fisheries Management and really refine these methods, and they're what we use today. So step 2, what do we do with all these data? Well, we collected information on density, how many fish are there, growth, how fast they're growing, and mortality, what's their survival rate. Now, I don't want you to get too lost in these figures. I just wanted to show these to illustrate that there's a lot of variation and variability going on both within lakes and across lakes. And we're going to talk about why that is in a minute. So I'm going to start with juvenile density. So over here I'm showing juvenile density on a log scale on the y-axis across a few of our study lakes. across months. And what you can notice is that, again, June and July have the highest catch rates, and that tends to taper off as the summer goes on. And that's due to emigration, fish leaving the system, and natural mortality. So what is this a result of? In short, the number of adults that make it into these systems really impacts how many offspring are produced. So we fit a generalized additive model like you can see here, looking at the juvenile density on the y-axis as a function of adult density on the x-axis. And what you can see is that it's a pretty linear relationship until it reaches an asymptote where there's a shotgun of points and quite a bit of uncertainty. And then what happens at the highest adult runs, the largest runs in the state of Massachusetts, for example, you start to see production and recruitment of these fish decline. And so what we've really identified is that adults can explain up to 65% of the variation in juvenile density. Really important factor, along with habitat availability and then the quantity of suitable habitat. I'm going to move on to growth. This is a similar figure looking at juvenile growth in millimeters per day on the y-axis, and again, select study lakes on the x-axis. And again, you can notice this variation. And what this is attributed to, in large part, is density-dependent growth. So in sites where there's a bunch of fish, really high densities, those fish are growing slower because there's less resources available to all the fish. And you have this really strong and prominent negative relationship between growth and density, which leads to really large variations of size at age. So for example, a fish caught in August from one system can be quite a bit smaller at the same age from a fish caught in a neighboring system, both geographically close and temporally close in time. And so you have these wild variations in size at age, which tend to set up later in the summer. I just want to note and highlight that otoliths are critical for these investigations. Otoliths are tiny little ear bones that all fish have, and they help with balance and a few other things. But they're beautiful, and they lay down these rings the same way a tree core would. So we go in and count these rings. We measure distances in between the rings to really ask and answer a lot of wonderful questions about length and age relationships, growth and mortality rates, spawning and hatch dates. So they can provide a wealth of information, and we use otoliths regularly. So step 3, how can we take the information that we are gathering from our long-term monitoring sites and apply it to what we might expect to happen at these restoration sites? So I'm going to highlight 2 complexes here that have had recent dam removals in 2017 and 2018. This is the Cotton Gin Dam that was removed on the Sawtucket River leading up to Robbins Pond, and then the Reed and Barton Dam, which was removed on the Mill River, that's leading up to Lake Sabbatia and Winnicunnet. Now I do want to quickly highlight Lake Sabbatia right down here, and then Winnicunnet is the site upstream of it, and we'll talk about that in a little bit. So first things first, in year 1 of sampling, we caught river herring. Removing the dam provided an immediate impact. These fish not only made it into the system, but they made it into the highest available headwater habitat. So you can see in 2018 this classic decline in densities that I alluded to earlier that we generally see across all sites, and fairly low catch rates. I'm showing the average catch per unit effort, so the average number of herring per haul that we caught on the y-axis. So again, highest in June, but we're catching single-digit herring as the summer progresses. Move on to 2019, and we see a little tick up in catch rates. So this is very encouraging because not only are fish now occupying these systems in year 1, the densities or the abundances are getting bigger in year 2, which is really something that's fascinating and that we want to continue to track. And we are seeing evidence that these fish are using the most upstream available habitat. So if you remember, Winnicunnet was upstream of Sabbatia, and you can see here in 2019, Winnicunnet has much higher densities than Sabbatia. would suggest that these fish are working their way upstream. And you could even see Sabbatia in July have a tick up for catch rates. And what that's presumably due to is fish that were spawned in Winnacunnet working their way back down the system. So really fascinating stuff. How does this compare to what's going on around the region? Well, these are still really low numbers. I'm showing, again, catch rates now across some of our regional sites. And on the bottom x-axis, you can see the estimated adult counts in parentheses. So we're still not anywhere near the thousands, hundreds of thousands of adults that get in to some sites, but we are seeing increasing numbers year after year, and it'll be really important to keep monitoring this trend. So, some walk-away conclusions. Survey methods that we've developed are critical to not only continue to monitor adult counts, but to couple that with juvenile surveys in their spawning and nursery habitats. It is achievable with high precision using a purse seine, but you have to do it in June and July, and you have to do it at night. Demographics. We saw a lot of variation within and among lakes. This variation seems to be steady from year to year within these systems, which can really help us inform expectations about what we might see in these restored sites. And again, density dependence, habitat quality and quantity are very important. As far as how these fish respond, they are colonizing restored habitats immediately. This is really encouraging news. Although they're in low densities, and you can see that fast growth right away relative to the low densities. So additional work is needed to monitor these trends, but it's really fascinating and encouraging to see what's happening immediately post-dam removal. So I have to leave it there, but I appreciate your attention, and I look forward to questions.
My name is Jim Turek. I'm a restoration ecologist with NOAA's Restoration Center in Narragansett, Rhode Island. Before I begin, I'd like to acknowledge my co-authors on this work, including Ms. Gail Fricano from Industrial Economics, Mr. Brandon Kulick from Kleinschmidt Associates, Dr. Dan Hayes from Michigan State University, Dr. Adrian Jordan from the University of Massachusetts Amherst, Dr. Mary Baker, and Dr. Jason Murray from NOAA's Assessment and Restoration Division. Our presentation is entitled Quantifying Fish Population Recovery Benefits from Dam Removals. As a roadmap for this presentation, I'll be presenting information on a model that has been a NOAA-led team has developed to help in quantifying fish population benefits. The presentation will include a brief background and project purpose information, followed by a discussion on the project literature review and expert elicitation components. I will then go over the model approach, limitations and assumptions, and model design and use. Through NOAA Fisheries, our agency trust resources include migratory fishes such as river herring and American shad that use East Coast rivers and streams to access spawning and rearing habitats. And our trust resources in the Great Lakes region include species such as lake sturgeon and walleye, which spend their entire life cycle in fresh waters, but migrate in rivers to reach spawning or overwintering habitats or for other life history purposes. To address the conservation and sustainability of these migratory fishes, NOAA has a matured restoration program targeting dam removals and other fish passage project types. NOAA is responsible through federal laws and regulations to participate in natural resource damage assessments, or NRDAs for short, resulting from oil spills or other contaminant releases. As part of the NRDA process, injury restoration is required of a responsible party or polluter to provide the equivalent of the natural resources lost, including interim losses accrued over time until pre-release baseline conditions are returned to the site. NOAA, as a trustee on behalf of the public, quantifies natural resource losses and gains, typically using what's called equivalency analysis. While NOAA's NRDA experience includes both many resource equivalency analysis, or REAs, and habitat equivalency analysis, or HEAs, we now seek to apply these techniques to quantify migratory fish population benefits from dam removals that result not only in fish passage and access to spawning and rearing habitats, but also restore and rehabilitate riverine habitats to increase habitat quality for these targeted species. Our overall goal is to implement dam removals that result in fish resource benefits equal to the fish species injured by the contaminant release. The first project component was to complete a thorough literature review of relevant source materials. We identified 36 publications on dam removal studies, 11 of which included before, after, control, impact study methods, while others included river reference sites for comparison to dam removal sites. Overall, most studies on fish population recovery have been relatively short term, with the longest being 7 years in addressing dam removals. We note that factors external to the targeted restoration site may also affect population recovery and must be considered in any model or other population assessment types. We also summarize the data gaps that remain relevant to the model development. These gaps include 1. Limited dam removal case studies with limited pre- and/or post-time series data or no reference site data. 2. A lack of studies on geospatial or geomorphic conditions of the river. 3. Consideration of factors external to the river and dam removal site. And 4. Confounding factors that relate to site-specific conditions and/or management actions. Our project team next completed an expert elicitation by engaging not only expert fishery biologists, an assessor, and resource economists from NOAA, but also academic and consulting fishery experts, modelers, biologists, and others with knowledge and experience in NERDs. We strengthen our elicitation approach by contacting and engaging 14 state and federal agency and NGO experts working on East Coast and Great Lakes fisheries and/or fish passage restoration. All persons were then engaged in 3 sequential webinars to iteratively discuss fishery data availability, a draft model approach, and lastly, the model development itself and its refinement. Our model is based on resource equivalency analysis, or REA, that measures services provided by specific fish over time, and benefits result with increases in the fish species population for the targeted river. Additionally, the model accounts for both habitat quantity and quality for that fish species, defined as the weighted usable area. Lastly, the model accounts for pre- and post-removal differences in major river areas associated with the proposed dam removal. The model applies Habitat Suitability Index, or HSIs for short, for each migratory fish species. HSIs are readily available for each of the East Coast and Great Lakes migratory fishes through documents published by the U.S. Fish and Wildlife Service. The model has a default fish density data available in the literature, but the user is allowed to input alternative density data or other habitat data. The model allows for site-specific field data if available to users, and which should be provided and/or supported by fishery scientists experienced in the targeted dam removal watershed and region. We note the limitations and assumptions associated with our model. First, it is a simplistic predictive model, and it is assumed the fish density for the restored river reach will be equal to the density of the reach downstream of the proposed barrier removal. Other assumptions that are that the targeted fish species is habitat limited, prey availability is not limiting, nor are marine environmental conditions limiting for those migratory anadromous species. Lastly, we recognize the importance of reference fish densities for the targeted river or from nearby surrogate rivers or watersheds. Here we summarize the model design, an Excel-based set of spreadsheets with tabs and drop-downs for users to input or for selection. The model currently includes data for 4 East Coast species, including alewife, blueback herring, and American shad, and 2 Great Lakes fishes, plus 2 freshwater mussel species. A template is also provided for users to input data available for alternative species not currently represented in the model. For river habitat changes, the model allows for up to 5 subareas each within the dam and impoundment area, the river reach upstream of the impoundment, and the river reach downstream of the dam. HSIs are calculated based on site-specific habitat data inputs. The model can also account for the presence of a fishway at a targeted passage site. To aid in the use of our model, a user's guide will be available. Finally, we note that this model aligns with an evolving paradigm supported by NOAA to complete habitat-based RIAs for future NERDA cases. We anticipate that this model will be available to the public in late 2020 for persons engaged in NERDA or perhaps other compensatory programs. We finish off our presentation with several screenshot examples of the model sheets. The upper left screenshot with the red oval depicted identifies 15 subareas that can be defined with habitat inputs as identified in the yellow tabs. The lower left screenshot depicts inputs for 5 variables associated with this example of an HSI for alewife. And lastly, the screenshot on the right is a benefits output presented in present value alewife years resulting from a hypothetical proposed project with a scaled project life of 100 years. Thank you all very much for listening to this presentation and the other 3 presentations in this session. All presenters will now be available for responding to your questions. Thanks for joining us today. Well, hopefully folks can hear us. Let's see if I can open up the chat box with questions. Okay, I'm not seeing any question. Let's take a look here. Okay, I'm having a little trouble. Let's see here. If anybody else wants to take a crack at it while I'm trying to figure out why I can't open this up.
I can see the questions. So maybe I'll start off with the ones that were addressed for my presentation.
Go ahead, Alex, if you wouldn't mind.
So one was, did we track the proportion of fish that entered the spawning ponds? The answer is yes, we did, although we only did it for one of the 2 years of the study. And in that year, we basically found no fish entering Chapman Pond. That's the first pond on the downstream end of the watershed. And then about 50% of the fish that we released above Potter Hill entering Watchog Pond. And then farther up into Warden Pond, about 30% of the fish made it up there. So I mentioned that fish kind of
take a left turn or a right turn into the tributaries that their ponds are in, and it's a significant amount of fish. We don't expect them all to go all the way up to the headwaters. So it's good, but it's interesting that Chapman Pond we had no fish going into, and we think that's because the outlet for that pond is very small. It's choked with weeds, and maybe there's a little bit of a bottleneck there. Second question for me was, did we track the proportion of fish, or sorry, that was the first one. Can you talk more about the different tools for evaluating fish passage and why there are large differences in fish detection between radio and pit tags? Well, there's lots of different tools. I don't have time to go into them. They involve video, they involve having grad students sit at the top of a fishway and count the fish going by, marking and recapturing, which essentially telemetry is. But telemetry, radio tags, pit tags is probably the preferred tool because it gives us the most accurate estimates. Now, having said that, I did note that there's a big difference between using pit tags and radio tags. And the reason is probably because pit tags are smaller. They're less of a burden for the fish to carry around with them. Radio tags tend to be larger. You tend to have an antenna hanging out the mouth. And we know there are behavioral effects on the fish that may reduce their performance. So as things go along, radio tags will get smaller. There are some now almost the size of pit tags. So as they do, we expect the results that we get with the two technologies to basically converge and give us a much better estimate. But again, the estimates that we do get are conservative. So when we see a high percent passage with either radio or pit tags, we're pretty encouraged that the percent passage is in fact pretty high. That's probably all the time I have for us, so I'll pass it on to the rest of you guys.
Okay, so Abby or Matt, do you want to, Matt, there's a question here. Can you speak to some factors of juvenile spawning habitat quality that can be observed and measured?
Sure, that's a great question. Thanks for asking. Yes, so temperature is this master variable that we're really considering as we've seen a really tight link between growth, these daily individual growth rates of these juveniles and daily temperature in the lakes. And what we're finding is that as these temperatures reach 25 degrees Celsius or so, growth really slows and dramatically. And so this past summer and the previous summers, we've recorded, especially this past summer, temps reaching upwards of 28, 29, 30 degrees Celsius surface water. So that's going to be a challenge for these fish. I'd say one of our most interesting results is the relationship with how many fish there are in these ponds and dissolved organic carbons. So I'll try and keep this brief. Get flushed in from the terrestrial landscape with rain events and other instances, and it creates this tannic, dark stained brown color that you might see when you're swimming or boating. And that, in short, can limit the light and heat penetration into the water column, and it limits primary productivity and it really changes where the thermocline sets up in these lakes. And so these layers of stratification where you have warmer oxygenated temperatures, or excuse me, warmer oxygenated water columns above the thermocline, and then you have more dense, cooler, anoxic water below that thermocline. And so we've typically treated available habitat as surface area in a lake or volume of water. But what we're starting to find out is that these fish really don't, in fact, well, they potentially don't use all that habitat all the time. You know, these juveniles are very sensitive to oxygen levels below 4 or 5 milligrams per liter. And so these thermoclines in these lakes set up, and below the thermoclines, you have anoxic cold temperatures that we think these provide really stressful conditions for these juveniles, really limiting them and their habitat to the upper part of the water column, which can be really minimal in some of these lakes in late summer. So yes, I think thermocline depth can be measured and probably should be measured to some extent, and then related to the dissolved organic carbons coming into the system along with temperature. So great question, thank you.
Let's see.
I can see my questions. Would you like me to read them?
Yeah, why don't you try Abby next?
Okay, so the question is, a height of 16-foot dam was converted to a stream. How did you make up the height and what did you make up the grade change with? So good question. The stream, so when the dam was removed, the extent of the restoration went very far upstream, and unfortunately I can't remember the exact number of feet upstream, but you're right, there's still elevation gain to make up. And so this was what Malone and McBroom designed when they designed the river restoration. So they put in a series of rock weirs. So they tried to use rock that fit in with the local geology. And so there are these curved structures. So the fish are still swimming up elevation, but instead of having it all in one place and the fish are then bumping their heads against the dam, that elevation is then gradually spread out over a longer distance. So they're just going up small jumps at a time. Of course, they're not jumping, they're swimming. So that was that question. And then the next question is, why after restoration do you see an increase in the amount of time spent in Billington Sea and more leaving the pond? Excellent question. I have a lot of data analysis I still need to do, but one possibility is that the fish, well, let's see, temperature could have had something to do with that, and I haven't analyzed that yet. But it could be that since the fish are moving through that section where there used to be a dam and now there's a restored river, that they're just getting up to the spawning pond faster earlier in the season than they might have been able to when there was a dam in place. And we're thinking it's really temperature mediated when the adult herring are leaving the spawning pond and heading back out to the ocean. And so if they're getting up there earlier, they could just be spending more time there and then moving back. Why were there more that left? It could just be a tagging effect. But it also could be that, again, if there's not, actually, you know what? I don't know. There's a lot of possibilities for that, but I think it's a big one could be the fact that there's not as much migratory delay when the dam was removed.
Let's see, Matt, there's a question. Is there significance to how much time that river herrings spend in their spawning pond? I guess that would be, well, either Matt or Abby, if you want to take a crack at that.
I'm sorry, can you say that one again?
Is there a significance to how much time that the river herrings spend in their spawning ponds? So I assume the question relates to why do adults stay in a pond for how long?
Yep. So theoretically, the more time they spend in the pond, the more opportunity they have to spawn. So the more opportunity they have to reproduce.
I agree completely, and I'll add, I'll play devil's advocate here that there can be a wide window of time that these adults stay in the pond from a week or two to months that we've surveyed. So there can be overlap in competition. So as offspring are produced and they're recruited, although they eat different size prey items, there is overlap in the diet. And so if you have low water conditions where adults maybe can't get out, let's say, or they just choose to stay and have a prolonged spawning period, then they may compete with their offspring or eat their offspring, and all sorts of complications can arise with that. So it's a tricky thing.
Well, there's a question here also for all of us or any one of us. In your work removing dams and studying or improving fish passage, do you see any opportunity for the return of wild Atlantic salmon in the Northeast region? I'll take a shot at this one, and certainly everybody else chime in. But you know, certainly we recognize the federal government basically ended the potential for restoring wild Atlantic salmon runs in southern New England anyways, and the focus is on the 8 remaining rivers in Maine that has become the target for trying to bring back wild salmon runs. I will say that the model that I spoke of earlier, the 4 species that I just did by chance not mention relative to this session is Atlantic salmon. And so we certainly have included that in our model right now. The difficult part of that is, of course, having good data to populate the model. But anyway, we have that is part of the model that will be released hopefully later this year. And anybody else want to say anything more about Atlantic salmon?
Yeah, I'll just add a little bit. And just in theory anyway, if you remove dams, you can remove a potential barrier to both upstream and downstream movement. If it's a large hydro dam, certainly it removes the potential for turbid mortality. And any large dam with a fishway, there's always some element of delay for upstream migrant adult salmon to find that fishway and pass it. So removing those sorts of threats, I think definitely has a beneficial effect, with at least within the freshwater portion of their life history. What a lot of recent research has shown, though, is that a large component of the mortality problem in Atlantic salmon happens out in the ocean environment. That's something we can't do a whole heck of a lot about, at least at this juncture. So if the focus is on working on things that we can do something about, then certainly dam removal is probably one of the more beneficial things that you can do with respect to freshwater survival and migratory timing. So I think there are definite benefits, but what it will result in near term with respect to restoration is yet to be seen.
Okay, thanks, Alex. Can you talk, and this is for all of you, can you talk more about the different tools for evaluating fish passage and why there are large differences in fish detection between radio versus pit tags? And so that sounds like Abby or Alex.
Go for it, Alex.
Yeah, I'll start maybe, and then Abby, you can finish. But we've been doing this for a long time, and we found that we use pit tags and radio tags as two different tools. Pit tags have a very limited detection range on the order of only meters. So we tend to use those in confined passageways like fishways or downstream bypasses, where we can monitor that small area very, very efficiently. And pit tags are very cheap, so we can tag lots of fish. And Abby can tell you about that part of it. Radio tags can be detected at a range of up to 1 kilometer. So if we have large rivers like the Pawcatuck or long reaches that we need to monitor over, then radio or acoustic telemetry is a favored technology there. But as I mentioned earlier, it has its drawbacks in that the tags are larger, they have to carry a battery, and they have behavioral effects on the fish. So I'll pass it to you, Abby. Tell them more about pit tags.
Yep, so my experience has been mainly with pit telemetry, and the benefits are you can tag a large number of fish. Because the tags are comparatively cheap, you can the tags are they're smaller, or at least they have been for a while, smaller than the radio tags or acoustic tags. So you can tag smaller fish. So in this case, it was a good body size to tag ratio for river herring. And then you can get really fine scale data. So if you want to know, if fish are having issues with, a particular section of river, you can really zone in on exactly where you want to look at.
Yeah. I'll also add about pit tags is that Abby's site was very small, a small stream, so we could cover the entire stream with a pit tag antenna. A large stream you couldn't do that with. The other advantage with pit tags is that they don't have a battery. They last as long as they stay with the fish. So you can get data on repeat spawners for 2, 3, 4 years afterward they've been tagged, which is extremely valuable data. You can't get that with the radio tag, which has a limited battery life. So everybody likes pit tags, and a lot of people have been using them for various studies, but I always warn them that they do have a limitation in terms of the range that you can pick up fish. You can only make a pit tag antenna so big. They're both meaningful tools for the study, but you have to apply them correctly.
Okay.
And if I may. Well, so I have an example of the advantage of having a tag without a battery. So one of the other questions was about fallback. And so why, actually I can't see it right now, but why did I get fish that we tagged that then didn't move upstream? And so the going theory is that one, they had just been scooped out of the water and measured and then tagged. And so all of that time out of the water might have reduced their motivation to move upstream. We did have a fallback antenna, so an antenna that would detect them if they moved downstream. There was also another pond, might not have been as high quality habitat, but there was a pond downstream of where they were released, so they might have decided to spawn there. However, many of those fish that fell back in 2018, we detected the next year. So they still had their pit tags and we set up antennas again. So we were able to see that they came back the next year. So they might have just decided to skip a year and come back.
Okay, well, this is all some great questions. Sorry we didn't get to all the questions today. What I would suggest is if people are very interested in learning more, we can follow up with everyone that still has questions that have not been answered to get you responses. If there's a lot of interest on this topic, we can also have another webinar at some other convenient time, and you can let us know. And certainly, I would look forward to that. So thanks everyone for joining this session today, and I hope you enjoy the rest of the sessions this afternoon and the rest of the week. So thank you, and talk to you later. Bye.
Thank you, everyone.
Thanks, everyone.
Bye.